Since 2017, the machine learning industry has followed a predictable engineering baseline to increase model capabilities. Just scale it up, add more parameters. Under classical scaling, memory is locked to algorithmic depth. Chart parameter count against capability, resulting in a 45-degree line. To make networks smarter, engineers stack deeper layers and widen dimensions, storing billions of unique weights. This creates massive parameter bloat. This physical constraint created a pervasive assumption in modern engineering. The consensus was that for a model to reason better, it had to be physically larger. Continuing this brute force expansion is hitting a wall. The hardware costs to train and serve trillion-parameter models are becoming a bottleneck for the future of AI architecture. Human cognition operates on a different logic. Our brains have a relatively restricted capacity for raw rote memorization. Yet, we execute complex, multi-step algorithmic reasoning using specialized circuits. A new approach called virtual logical depth, or VLD, manipulates the transformer's computation graph to emulate this efficiency. By holding a constant parameter count, VLD allows for scaling effective algorithmic depth completely independently of the model's memory capacity. Isolating the computation graph from the physical weights allows for specialized architectures that prioritize logic over storage. Reasoning becomes a function of processing cycles rather than physical volume. This schematic shows the standard transformer architecture. Note the stacked layout of the encoder on the left and the decoder on the right. These blocks are physically stacked, typically n equals 6. A token passes through the first block, finishes its computation, and must step up to the next layer in the sequence. In this design, each layer uses a distinct, unique set of weights for the queries, keys, and values. Looking closer at this diagram of the multi-head attention sublayer, we see where the parameter cost originates. The model maps dependencies across representation subspaces in parallel. Each attention head requires its own linear projections, which consumes vast parameter storage. The core limitation is purely architectural. In a standard transformer, the logic depth is tied one-to-one with the physical matrix depth. Vaswani's topology solved the problem of sequential recurrence, but it created a new problem. It made deep reasoning physically expensive. VLD addresses this by decoupling the tensor path from the physical layers using 3 routing topologies. First is sequence routing, which loops a token back through the exact same layer multiple times before moving forward. Cycle topology loops a token through a multi-layer block, then resets it to the beginning for another pass. Inverse cycle reverses the order on the second pass, ricocheting the data up and down the stack. Across all 3 patterns, the actual weight matrices stored in VRAM remain static. The model gains depth through routing, not by adding new parameters. We define this as effective depth, the total number of logic steps the token takes, regardless of how many unique physical layers exist. VLD transforms transformers into reasoning engines, scaling logic without the hardware overhead of parameter expansion. To prove this, we must verify that recycling parameters doesn't accidentally increase the system's raw memory. Researchers used an entropy experiment, forcing a model to attempt memorization of 640,000 uniform random numbers. Figure 4a shows the baseline. In standard models, the absorbed information entropy scales directly with the number of parameters. More weights equal more memory. But look at the results for the VLD models on the right. Despite massive increases in effective depth, the absorbed information entropy stays flat. The dashed lines for the 5 million and 20 million parameter models do not move upward. This proves physical weights hard code the memory capacity. Increasing effective depth via VLD provides more reasoning headroom without adding a single bit of raw storage. With the memory ceiling confirmed, the researchers measured actual reasoning performance using the synthetic IGSM benchmark. This dataset requires 15-step algebraic calculations. It's complex enough that the model cannot rely on memorized solution templates. It has to calculate the answer. This chart shows the performance gap between classical scaling and VLD topologies. A 50 million parameter model using cycle routing achieved 70.7% accuracy. It significantly outperformed the 150 million parameter standard model. This logic held even as complexity increased. VLD consistently outperformed classical models even when tasks required 21 steps of reasoning. Evidence shows we can scale a network's analytical logic completely independent of its physical parameter size. Synthetic math is one thing, But machine learning must also perform on chaotic, real-world data. To validate these findings, engineers applied the VLD routing to the Llama 3.2 3B instruct architecture. They rigorously tested the modified model on GPQA for graduate-level scientific reasoning and complex code generation in human eval. The results confirmed a universal performance uplift when applying cycle VLD compared to the natively scaled base model. There are architectural limits. VLD scaling is non-monotonic, meaning that at extreme effective depths, the model eventually hits a performance plateau. Even with those limits, the improvements are architecture agnostic. VLD provides a clear path to increasing reasoning capabilities in practical engineering. We no longer have to rely on the unsustainable growth of physical parameters to achieve better results. Determining compatibility in attention heads does not require a unique physical layer for every single logic step. This shift brings machine learning architecture closer to the biological efficiency of the prefrontal cortex, which prioritizes processing over storage. The future likely belongs to compact, heavily looped reasoning cores that connect to external retrieval systems for their domain knowledge. This revolutionary design permanently separates the high hardware cost of memory storage from the computational requirement of multi-step reasoning. The path to deeper reasoning no longer requires proportional growth in physical memory. We have the tools to scale the logic of a model without expanding its footprint.